Massive stones were moved across impossible distances without modern machinery. This video will teach you how to think like an ancient engineer. We are going to reverse engineer the forgotten logic behind history's most enduring mysteries. How did they achieve such precision with only simple tools? What hidden principles allowed their structures to stand for thousands of years? By the end, you will see the world through their eyes, gaining a powerful new perspective for solving modern problems. We will uncover the 7 core principles that guided these master builders, from their deep reading of natural patterns to a mindset that built for millennia. Their secrets hold the key to a more sustainable and resilient way of building. What forgotten wisdom do you think we need to rediscover most? This mindset represents a fundamental shift in how we perceive the world around us. Ancient engineers did not see a separation between the physical structure of a pyramid and the path of the stars it tracked. For them, engineering was a sacred language spoken through stone, a direct expression of cosmic order. They worked with a deep, almost intuitive understanding of natural forces, observing how water shaped stone over centuries or how the sun's shadow changed with the seasons. This knowledge, passed down through generations, became a living library of physics, written not in books but in practice. Their blueprints were not drawn on papyrus but encoded in ritual, song, and the very landscape itself. A river's bend dictated a city's walls. The winter solstice sunrise determined a temple's doorway. Every decision was multi-layered, serving a structural purpose, a spiritual function, and a communal need simultaneously. This is why their constructions feel so profoundly rooted in their place, as if they grew from the earth rather than being imposed upon it. They were masters of context, reading the environment with a clarity we often lose in our rush for speed and scale. To grasp their forgotten logic, we must quiet the noise of modern assumptions and learn to see the world through their eyes, where every stone, every angle, and every alignment tells a story far greater than its individual parts. This first principle begins not with tools but with a profound and patient stillness. Before a single stone was quarried, ancient engineers dedicated their lives to watching. They became intimate students of the world's rhythms, seeing patterns where we might only see chaos. Their greatest innovation was not a new type of lever, but a new way of seeing. They tracked the sun's slow march across the sky year after year until they could predict its exact position on the horizon for any given day. They noted how the moon's pull guided the tides and how specific stars heralded the changing seasons. This was not abstract astronomy, it was practical, vital knowledge. A temple doorway aligned with the winter solstice sunrise did more than create a dramatic beam of light. It marked the turning point of the year, a promise of the sun's return, woven directly into the architecture. Their observations extended far beyond the heavens. They studied how water carved its way through stone over centuries, learning which slopes were stable and which would erode. They watched how wind whistled through a mountain pass, shaping the design of ventilation shafts to cool entire structures without any mechanical aid. They noticed how certain animals avoided particular areas, perhaps sensing unstable ground or underground water, and used that knowledge to choose the safest foundations. This was a deep, embodied form of pattern recognition, a database built not from numbers on a screen but from generations of lived experience. Every decision was informed by this accumulated wisdom, a dialogue with the environment that ensured their structures worked in harmony with natural forces. This mastery of observation was the essential foundation, the quiet, patient work that made their later, more visible miracles possible. How different is this from our modern approach, where we often design first and then struggle to manage the environmental consequences later. This deep observation of natural patterns led directly to a second, equally profound principle: the use of a universal geometric language. Ancient engineers saw numbers and shapes not as dry abstractions, but as the very fabric of reality, a sacred code that connected the heavens to the earth. For them, a perfect circle was not just a shape, it was a symbol of the eternal cycle of the sun and seasons. A specific ratio was not merely a number, it was a key to unlocking harmony, found in the spiral of a seashell and the spacing of leaves on a stem. They believed that by building according to these cosmic rules, their structures would inherit the stability and beauty of the universe itself. This philosophy is brilliantly expressed in principles like the golden ratio, a proportion so pleasing to the human eye that it appears throughout nature and art. But for ancient builders, it was far more than aesthetic, it was structural wisdom. When they designed a temple, they did not simply decide on arbitrary dimensions. They used these sacred ratios to determine the relationship between a building's height and its width, the size of its doors relative to its walls. The result was a structure that felt inherently balanced and right, because its proportions mirrored those found in the world around us. The Parthenon in Greece is a classic example, where the application of these geometric rules creates an optical illusion of perfect straightness and harmony, even though there are almost no truly straight lines in its construction. This practice was known as squaring the circle, a geometric puzzle representing the union of earthly and divine. It was an attempt to create a square with the same area as a given circle, a symbolic act of bringing cosmic order into a tangible, human-made form. This was not just theoretical, it was applied philosophy in stone. The layouts of entire cities, from ancient Mesopotamia to the planned capitals of China, were often based on a sacred grid, aligning streets and walls with cardinal directions and celestial events. This geometric language provided a universal template, ensuring that every element, from the smallest carving to the grandest plaza, was part of a coherent, harmonious whole. The strength of their buildings came not just from the quality of their mortar, but from the perfection of their proportions, which distributed weight and stress in ways that mimicked the efficient structures of nature. Their blueprints were written in a language of angles and ratios that spoke directly to the laws of physics. This geometric language, however, would have remained mere theory without the physical means to translate it into reality. The true genius of these engineers was in their application of simple tools to achieve monumental results. They turned fundamental physics into a practical extension of human effort. With nothing more than a weighted string, the plumb bob, they could define a perfect vertical line against any surface, ensuring their walls rose straight and true for hundreds of feet. The water level, a simple tube filled with liquid, allowed them to establish a perfectly horizontal plane across vast distances, a principle we still use today. For laying out the grand foundations of cities and temples, they employed the groma, a clever surveying instrument that used suspended weights to sight precise right angles, effectively drawing massive geometric shapes onto the landscape itself. These tools were just the beginning. To move the colossal stones we marvel at today, they mastered the basic principles of mechanics. The lever allowed a small team to lift an incredible weight by creating a massive mechanical advantage. Systems of pulleys redirected force, enabling workers to pull loads upward from a safe and efficient position. But perhaps the most elegant solution was the inclined plane. Instead of attempting to lift a multi-ton block vertically, they would build a long, solid ramp of earth and rubble, and then simply drag the stone up the gentle slope. This method traded immense, instantaneous force for a slower, manageable application of power over a longer distance. The coordination required was immense, with teams of workers pulling on ropes in a rhythmic, synchronized effort that turned human labor into a precise, living machine. This understanding evolved into even more sophisticated technology. The Romans perfected the treadwheel crane, a massive wooden structure powered by men walking inside a giant wheel. This harnessed rotary motion to lift heavy stones with remarkable control. Similarly, the capstan, a rotating drum turned by pushing long bars, provided the torque needed to wind ropes and move enormous loads. Their innovation extended beyond moving objects to the very materials they used. Roman engineers developed a type of concrete that could actually harden underwater, a secret recipe that allowed them to construct harbors and bridges that have endured for 2 millennia. They also created specific metal alloys, blending copper and tin to produce bronze that was hard enough for durable tools yet resistant to corrosion. Even the Egyptians demonstrated profound material wisdom. To move giant statue bases on wooden sledges across the desert, they would pour water onto the sand in front of the sledge. This simple act drastically reduced friction, turning the sand into a slick, muddy surface that made the impossible task merely difficult. Their toolbox was not a collection of primitive implements, but a suite of perfectly adapted technologies, each one a masterful application of a fundamental law of nature. The true measure of their genius is not in the tools themselves, but in the breathtaking scale of the problems they solved. Consider the Roman aqueduct, a network of stone channels that brought fresh water cascading into the heart of cities, quenching the thirst of millions. To reverse engineer this marvel is to witness a perfect marriage of vision and precision. The objective was stunningly simple: to move water from a mountain spring to a distant urban center using nothing but gravity. But the execution required a level of planning that seems almost superhuman. Before a single trench was dug, teams of surveyors would walk the entire proposed route, mapping the land with an eagle's eye for detail. Their most crucial instrument was the chorobates, a long, carefully leveled wooden bench with water-filled grooves at each end. By sighting along this perfectly horizontal plane, they could determine the most gradual, consistent descent across dozens of miles of rugged terrain. The gradient they achieved is almost unbelievable to modern engineers, a slope of just a few inches per mile. This was not guesswork, it was mathematics made manifest in stone, a testament to their obsession with accuracy. Where the land dipped into a deep valley, a simple underground pipe would not suffice. Instead of diverting the entire route, they built soaring arcades of arches, carrying the water channel high above the ground. This solution reveals a profound understanding of structural forces. The arch is a masterpiece of efficiency, channeling the immense weight of the masonry downward and outward into its sturdy piers. But the Romans went further, developing a special concrete using volcanic ash known as pozzolana. This material possessed a miraculous property. It could set and harden even when completely submerged, allowing them to build foundations in rivers and create aqueducts that crossed marshy ground without sinking. The logic did not stop at delivery. Inside the city, the water first flowed into large sedimentation tanks, where heavier particles of silt and sand would settle to the bottom, clarifying the supply. From there, it was channeled to distribution points called casella, small, tower-like structures that acted as the plumbing hubs of the ancient world. From these casella, lead or ceramic pipes would carry water to public fountains, bathhouses, and even the private homes of the wealthy. This was not just an engineering project, it was a holistic system for public health and urban living, a network that turned a natural resource into the very lifeblood of a civilization. The aqueduct's success lay in its relentless, step-by-step logic, a chain of brilliant solutions that transformed a simple idea into an enduring wonder. Yet this mastery of scale and precision was not born from a single flash of inspiration. The myth of the flawless ancient genius obscures a far more human and relatable truth. Their engineering was a relentless process of trial, error, and iterative refinement. We imagine these colossal structures rising perfectly on the first attempt, but the archaeological record tells a different story. We find evidence of walls that were thickened after showing signs of stress, foundations that were reinforced after settling unevenly, and even entire structures that were rebuilt after a catastrophic collapse. These are not signs of failure, but of a deeply pragmatic intelligence at work. Each crack was a lesson, each collapse a brutal but invaluable teacher. This willingness to learn from mistakes created a cumulative body of knowledge where every project informed the next. Consider the Roman arch, that iconic symbol of their architectural might. Its perfect soaring form was not invented overnight. It evolved over centuries, beginning with the corbelled arches of earlier cultures, where stones were stacked in successively inward steps until they met at the top. This design was unstable. The Romans experimented, refining the shape into the true arch we recognize, with its precisely cut voussoirs, the wedge-shaped stones, all pressing against one another to channel weight downward into the supporting piers. But even then, they kept improving. They learned that a wider span required a different approach, leading to the development of the barrel vault, which is essentially an arch extended into a tunnel, and later the groin vault, created by the intersection of two barrel vaults, which distributed weight even more efficiently and allowed for larger, more open interior spaces like those in the Grand Roman baths. This was not a static adherence to tradition. It was a dynamic, living process of innovation. Their long-term perspective allowed them to invest in this gradual refinement, understanding that a small improvement tested on a bridge today could lead to a stable aqueduct that would serve a city for 1,000 years. This embrace of practical learning, of seeing failure as data rather than defeat, is perhaps one of the most vital lessons their forgotten logic holds for our own, often impatient world. How many of our modern solutions might be more resilient if we allowed for a cycle of observation, experimentation, and adaptation? This iterative process of trial and error forged a third vital principle, a deep symbiosis with the environment. Ancient engineers did not seek to conquer the landscape, but to collaborate with it. Their designs emerged from a profound dialogue with the land, working with natural forces rather than against them. This philosophy stands in stark contrast to modern projects that often begin by bulldozing a site flat, imposing a rigid blueprint upon the terrain. The ancient approach was one of adaptation and integration. In the American Southwest, the ancestral Pueblones built their magnificent cliff dwellings at Mesa, veered directly into the natural alcoves of canyon walls. These towering rock overhangs were not chosen at random. They provided a ready-made roof shielding the community from rain and snow. More brilliantly, the rock face itself acted as a natural thermal mass. It would absorb the sun's heat during the day and slowly release it through the night, moderating the extreme temperature swings of the desert, creating a comfortable living environment without any need for mechanical heating or cooling. This was not just building in a location, it was becoming a part of the location. Perhaps the most elegant example of this symbiotic logic is the Qanat system, an ancient Persian innovation for surviving in arid climates. In a desert, surface water is scarce and evaporates quickly under the hot sun. Instead of attempting to build massive, vulnerable canals, Persian engineers looked underground. They located water sources at the base of mountains and then, with astonishing precision, dug a gently sloping tunnel from the water source all the way to the surface many miles away. The slope was so gradual that gravity would pull the water along without eroding the tunnel walls. By keeping the water channel deep underground, they virtually eliminated loss from evaporation, delivering a steady, reliable flow to the surface for irrigation and drinking. This was a masterclass in hydrology and passive design, a solution that required immense upfront effort but then functioned for centuries with minimal maintenance. This principle demanded an intimate knowledge of the local environment, an understanding of geology to know where to dig, of microclimates to know where to build, and of ecology to know which resources could be sustainably used. They viewed the world as a living system of which they were a part. Their structures were not standalone objects but extensions of the landscape itself, designed to be as resilient and efficient as the natural world that supported them. In an age where we grapple with the consequences of dominating our environment, their forgotten logic offers a powerful alternative, a reminder that the most enduring solutions are those that flow with the grain of nature, not against it. The sheer scale of a single multi-ton block defies easy comprehension. Moving it across miles of rugged terrain seems like a task for giants, not for human hands. Yet the logic behind these megalithic marvels begins not with a miracle, but with a master plan, a blueprint for action that unified an entire community. The first step was always the quarry, where the raw material was selected with incredible care. At sites like the ancient Egyptian quarries in Aswan, we can still see the evidence of their methods. They would first identify a flawless section of bedrock, then use simple stone balls harder than the granite itself to pound a narrow trench around the intended block. This repetitive, exhausting work would eventually isolate the stone from the living rock. But how do you move a 50-ton obelisk from the quarry to a riverbank miles away? The answer lies in a combination of simple physics and immense human coordination. They likely used a system of wooden sledges, lubricated with water or mud to reduce friction, and pulled by teams of workers hauling on heavy ropes. This was not a chaotic tug of war. It required a rhythm, a synchronized pull, perhaps guided by a foreman beating a drum or chanting a cadence. The workers became a single, living machine, their collective effort transforming impossible weight into manageable motion. The final act of raising a massive stone into a vertical position was the most dangerous and ingenious of all. For the great trilithons at Stonehenge, the upright stones, each weighing many tons, were likely tipped into deep, sloped foundation pits. As the stone was pulled upright, its base would slide down into the pit, guided by timber frameworks and controlled by ropes from the opposite side to prevent it from toppling over. The horizontal lintel stones were then raised incrementally using levers and earthen ramps, a painstaking process of lifting, propping, and building the ramp higher until the stone could be slid into its final position. This entire endeavor, from quarry to placement, was a symphony of coordinated labor, a testament to a society that could plan decades, even centuries, into the future. The alignment of these structures with celestial events adds another layer of profound logic. The main axis of Stonehenge points to the summer solstice sunrise. The Great Pyramid of Giza is aligned with near-perfect precision to the four cardinal directions. This was not an afterthought. It means the entire construction process, the laying of the foundation, was dictated by astronomical observation. The builders needed to know exactly where to place the first stone, years before the final capstone was set, to ensure the finished monument would capture that specific beam of light on the longest day of the year. This integration of celestial knowledge into the very bedrock of a project reveals a mindset where practical engineering and spiritual belief were one and the same. The monument was not just a pile of stones, it was a calendar, a temple, and a cosmic clock, all built into one. The logic of stone and scale was therefore a logic of unified purpose, where every individual action, from the quarryman's swing to the astronomer's sighting, contributed to a vision that would outlast them all. But how could such intricate knowledge survive for generations without a single written blueprint? The answer lies in a fourth principle, a living chain of wisdom forged through oral traditions and deep apprenticeships. In a world before mass literacy, the master builder was not just an engineer but a storyteller and a teacher. He held the accumulated knowledge of centuries in his memory, a living library of techniques and principles passed down through a sacred line of succession. An apprentice would not simply learn by reading a manual. He would learn by doing, by watching, by listening for decades. He would mix mortars with his own hands, feeling the correct consistency. He would sight the stars alongside his master, learning the subtle signs that marked the turning of the seasons. This was knowledge transmitted through experience, becoming as instinctual as walking. To make this vast body of information unforgettable, it was often encoded within myths, songs, and rituals. The precise geometric layout of a temple might be taught not as a dry set of measurements, but as the story of a god pacing out the sacred boundaries of the world. The correct sequence for laying a foundation could be embedded in a chant whose rhythm mirrored the careful, deliberate steps of the work itself. This fusion of practical skill and symbolic narrative made the knowledge sacred, ensuring it was treated with reverence and passed on with meticulous accuracy. It created a powerful guild system, a closed circle of experts who maintained an unwavering standard of quality and a coherent design philosophy that could define an entire civilization's architecture for 1,000 years. This method was not foolproof. A war or a plague could break the chain and erase priceless knowledge forever. But when it worked, it created a depth of understanding that is hard to capture on paper. The apprentice did not just know that a certain arch would stand. He understood why, because he had felt the stones settle into place and had heard the stories of what happened when the proportions were even slightly wrong. This was knowledge written not on papyrus but in muscle memory and shared culture, a resilient and deeply human system for preserving genius. Buried beneath the waves for 2,000 years, a lump of corroded bronze and wood would rewrite history. The Antikythera mechanism, discovered in a Roman shipwreck off the coast of Greece, is not a statue or a simple tool. It is a machine, a complex clockwork of at least 30 interlocking bronze gears, housed in a wooden case no larger than a shoebox. For decades after its recovery, its true purpose was a mystery, its intricate workings fused into a single, unreadable mass. It was only with the advent of advanced imaging technology, like three-dimensional X-ray scans, that researchers could peer inside without destroying it. What they found was breathtaking. This was not a mere ornament. It was an analog computer, a device of staggering complexity designed to model the cosmos itself. By turning a hand crank on the side, the user could advance time forward or backward, and a series of dials on the front and back would display the ever-changing positions of the sun, the moon, and the 5 planets known to the ancient Greeks. It could predict lunar phases, solar eclipses, and even the timing of major athletic festivals like the Olympic Games. This was a portable planetarium, a mechanical calendar of celestial events, all powered by human hands. The very existence of such an object forces a complete re-evaluation of ancient technological prowess. We are accustomed to marveling at their static monuments of stone, but this reveals a world of moving parts, of precision engineering on a miniature scale. The logic encoded in its gears is a hybrid of brilliant traditions. It uses Babylonian arithmetic, centuries of meticulous astronomical observations recorded on clay tablets, to calculate the irregular motions of celestial bodies. But it translates these mathematical formulas into physical reality using Greek geometrical theories, employing a delicate ballet of precisely cut gears to mimic the cycles of the heavens. The ratios of the gear teeth are the key. A gear with 64 teeth meshing with a gear with 38 teeth creates a specific rotational relationship. The builders calculated these ratios with extraordinary accuracy to replicate the complex orbits of the Moon and planets, including subtle anomalies like the Moon's elliptical path, which causes it to speed up and slow down. They even included a clever pin and slot mechanism to account for this variation, a sophisticated differential gear system that was not thought to have been invented until the 16th century. The mechanism is a physical theory of the universe, a working model built from bronze. Its discovery is a stark reminder that the historical record is a collection of fragments, a tiny fraction of what once existed. This single surviving device implies a lineage, a school of thought dedicated to precision mechanics that has otherwise vanished without a trace. How many other such marvels were melted down for their bronze or simply decayed into dust? The Antikythera mechanism expands the very definition of ancient engineering. It shows us that their genius was not confined to the monumental and the immovable. They were also masters of the small, the intricate, and the dynamic, capable of building machines that could think, in their own way, about time and space. That intricate clockwork of bronze gears stands as a powerful testament to a fourth, equally vital principle: material intelligence. Ancient engineers did not see stone, wood, or metal as generic, interchangeable supplies. They understood them almost as living partners in their work, each with its own unique character, strengths, and hidden potentials. This was an intimate, almost conversational relationship with substance itself. A master builder would know that a particular type of granite, quarried from a specific hillside, had a grain that ran true and could withstand immense pressure, making it perfect for a pyramid's foundation blocks. He would know that another type of limestone was softer, easier to carve into intricate hieroglyphs for the inner chambers. This knowledge was not merely technical. It was born from generations of hands-on experience, from feeling the way a stone split under a hammer, from watching how a specific timber bent under stress or resisted rot over decades. They practiced a form of long-term foresight we often neglect, considering not just how a material would behave the day it was placed, but how it would weather, settle, and interact with adjacent materials over 1,000 years. The Roman development of pozzolanic concrete is the ultimate expression of this intelligence. They did not invent a new material from scratch in a laboratory. Instead, they looked at their local environment with brilliant insight. They noticed that volcanic ash, a plentiful resource around Rome, when mixed with lime and water, created a paste that possessed a miraculous property. Unlike modern concrete, which weakens when submerged, this Roman concrete actually gained strength in contact with water, forming a crystalline structure that could endure the relentless pounding of ocean waves. This was innovation born from a deep understanding of local materials, a perfect alignment of need and available resource. They were not forcing a substance to conform to a rigid design. They were listening to what the material itself could do and then designing accordingly. This principle extended to every facet of their work. Wood was not cut and used immediately. It was carefully seasoned, left to dry slowly and naturally to prevent it from warping or cracking after being placed in a structure. Metals were not just melted, they were alloyed, blending copper with tin to create a bronze that was harder and more durable than either metal alone. This material intelligence was the silent partner to their geometric genius. The most perfectly proportioned arch would still collapse if made from the wrong kind of stone. Their forgotten logic was therefore a dialogue between ideal form and physical reality, a conversation where the inherent wisdom of the material was given the final say. This material intelligence was only half the equation. The most brilliant design, carved into the most perfect stone, would remain forever in the quarry without a force to set it in motion. That force was human society itself. The true engine behind every ancient wonder was not just physics, but people, organized on a scale that still staggers the mind. The logic of stone was inextricably linked to the logic of community. Think of the Great Pyramid of Giza. For generations, we pictured armies of slaves driven by the lash. But the archaeological evidence paints a far more compelling picture. The workers' villages excavated near the site reveal not squalid prison camps, but organized communities with bakeries, breweries, hospitals, and homes for skilled laborers and their families. These were not slaves, but most likely a rotating workforce of Egyptian farmers. During the annual inundation of the Nile, when their fields were flooded and farming was impossible, the state mobilized this vast, idle labor force for national projects. In return, they received food, shelter, and perhaps a sense of participation in a grand, divine mission. This was a sophisticated system of labor management, a way to turn a seasonal pause in agriculture into productive, nation-building work. The logistical challenge was monumental. Feeding 10,000, perhaps 20,000 people, day after day for decades, required an administrative machine of breathtaking efficiency. Scribes kept meticulous records on papyrus, tracking the delivery of cattle from the Delta, boatloads of grain from Upper Egypt, and shipments of tools from workshops across the country. This was a supply chain stretching the entire length of the Nile, all converging on the Giza Plateau. The project required not just unskilled muscle, but a whole ecosystem of specialists, quarrymen who understood how to split granite, carpenters who built the sledges and ramps, water carriers who kept the workforce hydrated, and cooks who prepared thousands of loaves of bread daily. The motivation was a powerful blend of the spiritual and the practical. For the individual worker, building a pharaoh's tomb was an act of religious duty, a service to a god-king that would help ensure the cosmic order and their own place in the afterlife. For the state, it was a demonstration of absolute power and organizational capability, a project that unified the country under a single, visible goal, creating a national identity literally set in stone. This social engine, whether driven by faith, duty, or decree, was the invisible framework upon which the visible marvel was built. The pyramid's enduring strength comes not only from the precision of its blocks, but from the coherence of the society that raised them. That invisible social engine was driven by a fuel far more potent than simple economics, a profound and unifying cosmology. The logic of ancient engineering was not a cold calculation of forces and materials. It was a sacred act, a deliberate effort to mirror the perceived order of the cosmos in stone and mortar. A temple was never just a building to provide shelter from the rain. It was a carefully constructed microcosm, a physical representation of the universe itself. This spiritual imperative provided a powerful, non-negotiable design framework that dictated every single aspect of construction, from the grandest alignment to the smallest measurement. In ancient Egypt, the cardinal directions were not arbitrary. East, the place of the sun's rebirth each morning, was the direction of life, while west was the realm of the dead. Therefore, a temple's main axis had to be precisely oriented east-west, aligning the pharaoh, a living god, with the solar cycle that guaranteed the kingdom's continued existence. This was not a vague suggestion. It was a rigid requirement that demanded incredible surveying precision long before the foundation stone was laid. The very dimensions of these structures were often derived from sacred numbers or astronomical cycles. The height of a pyramid might correspond to a specific astronomical unit, or the ratio of its base to its height might encode a fundamental mathematical constant believed to be the key to cosmic harmony. This integration of belief and building created a powerful feedback loop. The need for celestial alignment forced engineers to develop more accurate astronomical tools and surveying techniques. The desire to build on a cosmic scale pushed the limits of material science and labor organization. What might appear to a modern mind as a constraint, a set of arbitrary religious rules, actually served as a rigorous creative discipline. It prevented aimless experimentation and focused immense intellectual and physical resources on achieving a single, coherent vision. Nowhere is this fusion more vivid than in the stepped pyramids of Mesoamerica. Each level of the pyramid was not merely a structural tier, it represented a different spiritual plane in the layered universe of Mayan or Aztec belief. The climb to the summit was a symbolic journey from the earthly realm to the heavens, a reenactment of a mythic ascent. The number of steps, the placement of altars, the orientation of the stairways, all were dictated by this cosmic map. The engineering challenge was to make this symbolic vision a stable, physical reality. The result was a structure that was both geometrically sound and spiritually resonant. Its strength derived as much from its symbolic coherence as from the quality of its masonry. This mindset meant there was no separation between the engineer and the priest, between the architect and the astronomer. They were often one and the same, or worked in such close collaboration that their knowledge became indivisible. The technical necessity of a thick wall to support a heavy roof was seamlessly blended with the spiritual necessity of that wall being inscribed with hieroglyphs that told the story of creation. The practical need for a drainage system in a temple courtyard was integrated into a design that channeled rainwater in a way that symbolized the annual flooding of the Nile, the source of all life. For the ancient engineer, the highest purpose of their work was to build a bridge between the human and the divine, to create a space where cosmic order became tangible. Their forgotten logic was, therefore, a holistic one where faith provided the blueprint and engineering became the method of its sacred construction. Even with all our modern tools and knowledge, some ancient techniques defy easy explanation. These are the stubborn mysteries, the gaps in the historical record that remind us how much specialized, hands-on wisdom has been lost. Take the stone walls of the Inca high in the Andes. The precision is simply mind-boggling. Massive blocks of granite, some weighing many tons, are cut into irregular, interlocking shapes. They fit together so perfectly that you cannot slide the edge of a razor blade into the seams. No mortar was used, and yet these walls have withstood centuries of earthquakes that have flattened modern buildings all around them. How did they achieve such an exact fit? We have theories, of course. Perhaps they used a method of trial and error, repeatedly lowering one stone onto another and marking the high points for further grinding with simple stone tools and abrasive sand. But the speed and consistency of the work remain a subject of intense debate. It suggests a level of practical geometry and tactile skill that we have yet to fully replicate. Then there are the legendary materials themselves, whose secrets were so closely guarded they died with their masters. The famed Damascus steel, used to forge swords of incredible strength, sharpness, and beauty, with a distinctive wavy pattern like flowing water. The original recipe is lost. We know it started with a special type of iron ore from India, known as Wootz steel, but the exact process of heating, folding, and cooling that gave the metal its unique crystalline structure remains elusive. Modern metallurgists can create similar patterns, but they have not perfectly matched the legendary combination of hardness and flexibility that could supposedly cleave a silk scarf floating in the air. Similarly, the formula for Greek fire, a terrifying incendiary weapon used by the Byzantine Empire, was a state secret of such importance that it was never written down. It was said to burn on water and could only be extinguished with sand, vinegar, or urine. Was it a primitive form of napalm, a mixture of petroleum and quicklime? We simply do not know. Its exact composition was known only to a select few, and when that chain of knowledge was broken, the formula vanished forever. Other mysteries are not about what is lost, but about an understanding we are still struggling to measure. The acoustics of ancient Greek theaters, like the one at Epidaurus, are a perfect example. This open-air stone theater, built over 2,000 years ago, possesses near-perfect acoustics. A performer speaking in a normal voice on the stage can be heard clearly by every one of the 14,000 spectators, even those in the very back row. For years, engineers assumed the steep slope of the seating acted as a natural sound filter, but recent studies suggest the secret may lie in the limestone seats themselves. The porous stone might be filtering out low-frequency background noise, like the murmur of the crowd, while simultaneously reflecting the high-frequency sounds of the human voice. It is a brilliant, passive acoustic system built right into the material of the theater. This was not magic, it was an applied science of sound that we are only now beginning to appreciate with our sensitive digital equipment. These enduring puzzles are not just historical curiosities. They are humbling reminders that ancient knowledge was not a single, monolithic library. It was a vast constellation of specialized guilds, each holding deep, practical secrets that were passed from master to apprentice through demonstration and memory. When that living chain was broken by war, famine, or simply the passage of time, that particular branch of genius could be extinguished forever. These gaps in our understanding challenge the very idea of linear progress. They force us to admit that in some specific, refined areas, the ancients achieved a level of mastery that our own technology, for all its power, has not yet rediscovered. The detective work continues not as a search for lost superiority, but as a conversation with the past, an effort to listen to the faint echoes of a forgotten logic that still has something to teach us. That long-term perspective crystallizes into a fifth, monumental principle, the logic of the long now. Ancient engineers operated on a timescale that is almost unimaginable to us today. They did not build for a decade or even a century. They built for millennia, constructing with the explicit intention that their work would endure long after their names were forgotten. This was not a hopeful wish, it was a core design parameter that influenced every single decision, from the quarry to the capstone. It demanded a form of foresight that considered how materials would weather over 1,000 years, how foundations would settle across generations, and how a structure would continue to serve a civilization they would never see. The Roman roads that still form the foundation of European transport networks were not quick gravel paths. They were multi-layered masterpieces of durability. Workers would first dig a deep trench, then lay a foundation of large stones. On top of this, they placed a layer of smaller rocks mixed with rubble, followed by a course of finer gravel, and finally a smooth, cambered surface of tightly fitted paving stones. This intricate, labor-intensive process ensured proper drainage and a stable base that could withstand the weight of armies and trade caravans for centuries. They were literally building down to the bedrock, investing an immense initial effort to create an asset that would pay for itself 1,000 times over through uninterrupted use. This is the essence of the long now calculus, where the true cost of a project is measured not in the currency of its construction, but across the vast expanse of its operational life. They willingly over-engineered for durability, understanding that a slightly thicker wall, A deeper foundation or a more durable stone would cost more upfront but would prevent catastrophic failure and endless repairs in the future. The aqueducts, again, are the perfect example. A steeper, cheaper channel would have delivered water faster but would have eroded quickly from the force of the flow. Instead, they chose that miraculously gentle gradient of just a few inches per mile, a decision that required phenomenal survey work but resulted in a system that ran smoothly for hundreds of years with minimal maintenance. This mindset represents a fundamental divergence from much of modern engineering, which is often governed by short-term budgets and the concept of planned obsolescence, where products are designed with a limited useful life. The ancient logic asked, how can we make this last forever? Our contemporary logic often asks, how can we make this last just long enough? This shift in perspective is profound. Building for the long now required a societal stability and a cultural continuity that allowed for such vast projects to be initiated, knowing they might not be completed within a single ruler's lifetime or even a single generation. It was an act of faith in the future, a testament to a civilization's belief in its own endurance. The pyramids were not just tombs for a pharaoh, they were permanent statements of a kingdom's power, designed to be visible for all time. In an age facing challenges like climate change and resource depletion, this forgotten principle may be the most vital one to rediscover. It asks us to expand our vision, to consider what we are building that will still be standing and still be serving humanity 1,000 years from now. This seamless fusion of the spiritual and the structural reveals a sixth guiding principle, where aesthetic elegance was itself a measure of engineering success. Beauty was not applied like a coat of paint to a finished design. It was baked into the very calculus of the project from the very first sketch in the sand. Consider the subtle intosses of a Greek column, that almost imperceptible swelling along its shaft. To the naked eye, it appears perfectly straight, but this gentle curve is a deliberate optical correction. A truly straight column would appear to narrow in the middle when viewed from a distance, creating an illusion of weakness. The subtle bulge counteracts this, making the column look robust and unwavering, a testament to an engineer's understanding of human perception. Even the fluting, those vertical grooves carved into the stone, serves a dual purpose. While they create a beautiful play of light and shadow, they also reduce the visual weight of the column, making the massive stone structure seem to soar with a graceful lightness. This was engineering that considered the human eye as part of the load-bearing system. The same holistic logic applies to the Roman arch. Its soaring, semicircular form is the pinnacle of structural efficiency, channeling immense weight down into its supporting piers. But that same curve also creates a powerful psychological effect, framing a space with a sense of grandeur and arrival. The arch is not just strong, it feels strong. This interdependence meant that any change made for aesthetic reasons had to be vetted for its structural implications, and any structural adjustment had to be evaluated for its visual harmony. There was no room for error because a flaw in one area was a flaw in both. This philosophy created a built environment where everything felt right because it was right. The proportions were derived from natural patterns, the forms were optimized for both strength and grace, and the materials were chosen for their enduring beauty as well as their durability. In this worldview, a clumsy, purely functional structure was not just ugly, it was suspect. It hinted at a fundamental misunderstanding of the natural laws of balance and proportion. A truly stable bridge, a truly enduring temple, would inevitably express the same harmony found in a branching tree or a spiral galaxy. Beauty was not a luxury, it was the audible signal that the engineering was correct. This is why their ruins still move us today. They are not just piles of old stone, They are the physical manifestation of a principle we have largely forgotten, that the truest function is inseparable from a profound and lasting form. Their voyages unfolded across an ocean so vast it defies the imagination, a watery expanse covering nearly a third of our planet. The Polynesian expansion was not a haphazard drift, but a deliberate, masterfully engineered campaign of discovery. To reverse engineer their success is to understand a system where the boat, the sailor, and the sea itself were inseparable parts of a single machine. The foundation of this system was the Wa Kolua, the double-hulled canoe. Imagine two sleek hulls, each carved from a single massive log, connected by a strong wooden platform. This design was a stroke of genius. A single-hulled boat in the open Pacific would be dangerously unstable, vulnerable to capsizing in the powerful swells. But the twin hulls provided immense stability, acting like outriggers for each other. The platform between them offered crucial space for storing all the necessities for a voyage that could last for weeks: food, water, living quarters, and even seedlings and animals to start a new life on an undiscovered shore. These vessels were not crude rafts, they were sophisticated pieces of marine engineering, with woven sails that could be adjusted to harness the wind from any direction. Yet the canoe itself was only half the technology. The true marvel was the navigational system, a form of dynamic engineering applied not to stone or metal, but to information and environment. Without compasses, sextants, or maps, Polynesian navigators embarked on journeys across thousands of miles of trackless ocean, guided by a deep, accumulated reading of natural signs. They were living supercomputers processing a constant stream of environmental data. Their primary tool was the star compass, a mental map of the heavens where specific stars were known to rise and set over particular islands. As one star dipped below the horizon, the navigator would already have identified the next one rising to take its place, maintaining a constant celestial bearing through the night. But the sky was not always clear. During the day or under cloud cover, they switched to reading the ocean itself. They became experts in wave piloting, feeling the subtle patterns of swells reflected and refracted by distant islands. A seasoned navigator could sense a landmass beyond the horizon by the way the deep ocean swells interacted with the shallower water surrounding an island, creating a specific interference pattern that was felt through the motion of the canoe. They watched the flight paths of birds, knowing that certain species would fly out to sea to fish in the morning and return to land at dusk, revealing the direction to safety. Even the clouds played a part, a stationary bank of puffy clouds often gathering over the lush, high islands that created their own weather. This was not a collection of separate tricks, but a fully integrated system, a dynamic feedback loop between the navigator's senses and the environment. The knowledge required was immense and could only be preserved through an unbroken oral tradition. Master navigators, called PWO, would spend decades training apprentices, not in classrooms but on the open ocean, teaching them to feel the waves and memorize the star paths through song, story, and direct experience. This was engineering logic applied to the ultimate non-static challenge, navigating a fluid, ever-changing medium with nothing but human intellect and inherited wisdom. Their canoe was more than a vessel, it was a vehicle for a vast cognitive map, a testament to the power of engineering a system in perfect harmony with the natural world. That same principle of dancing with natural forces found its most urgent expression in the shadow of catastrophe. Ancient engineers were not just building for harmony, they were building for survival in a volatile world. Their logic was forged in the crucible of disaster, where a single earthquake or flood could erase an entire city. This constant threat forced a profound and practical adaptability, turning the memory of past collapses into a blueprint for future resilience. In the earthquake-prone islands of the Aegean Sea, the Minoan civilization constructed multi-story palaces with a remarkable feature: flexible foundations. They would lay a course of alternating stone and timber beams beneath their massive walls. During a tremor, the wooden beams would compress and absorb the energy, allowing the entire structure to shift and settle without shattering. Their doorways were not rectangular but trapezoidal, wider at the base and narrowing toward the top. This simple geometric change prevented the stone lintel from being easily dislodged by side-to-side shaking. High in the Andes, the Incas applied a similar logic on a grander scale. Their iconic, mortar-less masonry, with its intricate, interlocking blocks, was not just a display of precision. It was a highly sophisticated anti-seismic system. When the ground shook, the stones in the wall would subtly shift and grind against each other, dissipating the earthquake's energy. Instead of acting as a single, rigid mass that would crack under stress, the wall became a dynamic, flexible membrane that could sway and then settle back into place once the tremor passed. Their structures were designed to move with the earth, not fight against it. Meanwhile, in the floodplains of Mesopotamia, the engineering challenge was water. The same rivers that gave life to the Fertile Crescent could also destroy it with devastating seasonal floods. The response was not to retreat from the water, but to manage it with breathtaking ingenuity. They constructed vast networks of canals that served a dual purpose. In dry seasons, these channels irrigated the fields, turning the desert green. But when the floods came, the canals acted as a release valve, diverting the destructive excess water away from settlements and into controlled catchment basins. They built raised cities on immense mud brick platforms, lifting their homes and temples above the predictable high water mark. This was a form of predictive engineering, learning from centuries of observation to understand the river's rhythms and moods. They saw the destructive power of nature not as an enemy to be conquered, but as a force to be channeled. This reactive intelligence, born from necessity, demonstrates a crucial aspect of their forgotten logic: the ability to learn from failure and innovate under pressure. Their greatest innovations in durability often emerged from their most profound vulnerabilities. In an era of increasing climate instability, this ancient wisdom holds a powerful lesson. It teaches us that resilience is not about building higher walls against the storm, but about designing systems that can bend, absorb, and adapt, just as those ancient stones learned to dance. Yet for all our sophisticated scans and structural models, we inevitably hit a wall. We can reverse engineer the physical object, but we can never fully reconstruct the world that gave it purpose. This is the fundamental limit of our quest, the unbridgeable gap between knowing how something was built and understanding why it was built that particular way. Our analysis of the Antikythera mechanism can tell us the gear ratios with stunning accuracy, but it cannot let us hear the philosophical debates that inspired its creation. We can calculate the precise angle of a pyramid slope, but we cannot feel the religious awe that compelled a society to dedicate generations to its completion. This is a problem of context. The most crucial component of any ancient engineering project was not the stone or the bronze, but the invisible framework of beliefs, values, and shared knowledge that surrounded it. We are trying to read a book where most of the pages have been lost, and we are left inferring the entire plot from a few surviving paragraphs. Our modern perspective acts as a filter, unconsciously shaping our interpretations. We might see a clever labor-saving device where an ancient engineer saw a ritual necessity. We might interpret a structural choice as purely practical when it was deeply symbolic. Why was a specific type of wood used when a stronger one was available? Perhaps its choice had nothing to do with tensile strength and everything to do with its sacred association with a particular deity. Why was a temple aligned to a star that seems insignificant to our charts? That star might have been the celestial anchor for an entire creation myth, a meaning that has evaporated over the centuries. Some knowledge was never meant to be written down, guarded as the secret wisdom of a guild, transmitted only through demonstration and initiation. The master stonemason's trick for finding the perfect cleavage point in a granite block died with him, a tactile skill that no blueprint could ever capture. This is not a failure of our technology, but a reminder of the profound humanity of these endeavors. They were not created by dispassionate robots applying pure physics. They were created by people whose decisions were woven from countless threads of culture, spirituality, and practical law. To acknowledge this limit is not to admit defeat, but to approach the past with a necessary humility. The silent stones can tell us much, but they cannot whisper their deepest secrets. They remain magnificent puzzles, inviting us to learn not only about their construction, but about the vast, beautiful, and ultimately unrecoverable worldviews that brought them into being. That silent, unrecoverable worldview was nevertheless channeled into systems of astonishing efficiency. Across the sprawling expanse of the Roman Empire, a different kind of logic took hold, one designed for speed, scale, and unwavering consistency. This was the sixth principle, the logic of replication through standardization and modularity. The Romans understood that to build and maintain an empire, you needed more than grand visions, you needed a repeatable process. They turned construction into a kind of pre-industrial mass production. Instead of every brick being a unique, hand-shaped object, they were manufactured to strict standard sizes. A brick made in Gaul would fit perfectly with a brick made in North Africa. The same went for roof tiles, water pipes, and even the decorative capitals that topped columns. This meant that components could be prefabricated in centralized workshops, often run by the military, and then shipped to construction sites across the known world. A commander on the frontier did not need to wait for local artisans to figure out how to make a roof. He simply ordered a shipment of standard tiles. This was a revolution in logistics. It transformed building from a bespoke craft into a system of interchangeable parts. The ultimate expression of this modular thinking was the Roman military camp, the castrum. Wherever the legions marched, they would lay out an identical grid. The same streets, the same positions for the commander's tent, the granaries, and the barracks, all arranged according to a master template. This was not just about military discipline, it was a profound logistical advantage. A soldier transferred from the damp forests of Germania to the dusty hills of Judea would immediately know his way around the new camp. Supplies could be routed efficiently because every camp had the same layout. This modular design could be scaled up or down, from a temporary overnight fort to a permanent stone fortress, all based on the same core blueprint. This standardization did not create a bland, monotonous empire. Instead, it provided a reliable, stable foundation. Once the essential, repeatable elements were in place, local architects could and did add layers of regional flair and decoration. The underlying system ensured structural integrity and functional clarity, while the surface allowed for cultural expression. It was a balance between imperial control and local identity, all made possible by a shared language of measurement and form. This ancient principle of modular thinking is the direct ancestor of everything from the assembly line to modern software code, where standardized components are assembled into infinite variations. The Romans knew that to build something vast enough to last, you first had to master the art of the repeatable unit. That same search for durable concrete has led modern scientists back to the Roman recipe. For decades, we assumed our own Portland cement was superior. yet structures built with it often show significant decay within 50 years. Meanwhile, Roman piers have endured 2,000 years of pounding saltwater. The secret, it turns out, lies in the chemistry of their volcanic ash mixture. When seawater seeped into the Roman concrete, it actually reacted with the ash and lime to form a rare mineral called aluminous tobamorite. This mineral effectively fills in micro-cracks as they form, creating a material that can heal itself. Modern researchers are now actively developing self-healing concretes inspired by this ancient process, embedding capsules of healing agents or using bacteria that precipitate limestone to seal fractures. This is not mere historical curiosity. It is a direct application of ancient material intelligence to solve a modern crisis of infrastructure decay. The logic of building for millennia is literally being reborn in laboratories today. This principle of passive climate control, so evident in the cliff dwellings of Mesa Verde, is experiencing a powerful resurgence. The high costs and environmental impact of mechanical heating and air conditioning have driven architects to look back at ancient solutions. The term for this is passive house design, a standard that prioritizes a building's orientation, insulation, and thermal mass to maintain a comfortable temperature with minimal energy input. It is the modern equivalent of building a structure into the side of a cliff. By strategically placing windows to capture the low winter sun while shading them from the high summer sun, and by using dense materials like stone or tile to absorb and slowly release heat, these buildings achieve a remarkable stability. They are applying the ancient understanding that the sun's path is the most reliable and free climate system we have. This philosophy extends to ventilation, where clever designs create stack effects, drawing cool air from low openings and expelling warm air from high vents, just as ancient engineers did with wind-catching towers. This is not a rejection of modern technology, but a smarter integration of it, using ancient logic as the foundational layer upon which modern efficiency is built. This approach finds its ultimate expression in the field of biomimicry, a discipline that consciously echoes the ancient practice of deep observation. Engineers now study the structure of a termite mound to design more efficient building ventilation systems, just as ancient builders might have observed ant colonies. They analyze the microscopic structure of a lotus leaf to create self-cleaning surfaces, or the shock-absorbing geometry of a woodpecker's skull to improve protective gear. This is a formalized scientific return to the first principle, the idea that nature holds the blueprints for the most elegant and efficient solutions. The most profound shift, however, may be the renewed embrace of the long-term perspective. Organizations like the Long Now Foundation are championing projects with a 10,000-year vision, such as building a clock designed to tick for that entire duration. This challenges the short-term economic thinking that dominates so much of modern engineering and asks us to consider the legacy of our creations with the same gravity as the pyramid builders. The dialogue between past and present is no longer a one-way street of admiring ruins. It has become a vibrant, two-way conversation where ancient failures teach us about resilience, and ancient successes illuminate paths to a more sustainable future. By looking backward, we are not retreating, we are reclaiming a wisdom that allows us to move forward with greater foresight and humility. This relationship between the engineer and the state brings us to a profound and necessary question, one that lies at the heart of our quest. The stones of these monuments are silent on the matter of human cost. The sheer scale of the Great Pyramid required a social engine of immense power, one capable of mobilizing tens of thousands of people for decades. While the evidence points more toward a state-sponsored workforce of conscripted laborers than outright slavery, the reality remains one of extreme social stratification. The pyramid was built by the many for the singular glory of one, a god-king whose authority was literally set in stone by the project itself. This forces us to confront an uncomfortable duality. The undeniable technical brilliance of the engineering stands in stark contrast to the social system that made it possible. Can we truly admire the achievement while acknowledging the human toll? This is not a question with an easy answer, but it is an essential part of reverse engineering their complete logic. To understand how they built is to also understand why they built and for whom. The ancient engineer's genius was almost always in the service of consolidating power, whether for a pharaoh, an emperor, or a priestly class. Their aqueducts quenched the thirst of Roman cities, but they also secured the loyalty of the populace to the empire. Their majestic temples inspired awe, but they also reinforced a cosmic order that placed the ruler at its center. The application of knowledge was never a neutral act. It was a tool of statecraft, a means of control, and a declaration of dominance. This inextricable link between technical knowledge and political power is a lesson that echoes loudly today. Our modern technologists wield a different kind of power, from shaping global communication networks to developing artificial intelligence. The same ethical dilemma applies. The brilliance of the code or the algorithm does not exist in a vacuum. It is embedded in a social and political context, and its application is a moral choice. Will a new technology be used to empower or to control, to liberate or to surveil? The ancient world reminds us that engineering is a form of power, and with that power comes a deep responsibility. To rediscover their forgotten logic is not just to learn their techniques, but to grapple with the enduring truth that how we build, and for whom, defines the legacy of our creations as much as their structural integrity. Scarcity was not a barrier, it was the very engine of their brilliance. This seventh principle reveals a profound paradox, the power of constraints. For the ancient engineer, a limited toolbox was not a frustration but a creative catalyst. Without cheap, abundant iron for structural beams, they had no choice but to master the logic of stone, learning to balance immense weights through perfect geometry and friction. The absence of fossil fuels forced an intimate understanding of natural energy flows. They could not simply overpower a problem with a diesel engine, so they learned to harness the relentless push of the wind for sailing and milling, the predictable flow of water to turn wheels, and the coordinated strength of human and animal labor. Every solution was born from a necessity to do more with less, to extract the maximum possible effect from the minimum possible input. There was no room for waste, either in material or in motion. A block of stone was cut with such precision that the offcuts could be used for smaller elements. The path of a sled carrying a monument was planned to avoid any unnecessary incline. This relentless efficiency was not a choice, it was a mandate imposed by the physical reality of their world. In our age of apparent abundance, where inefficiency can be masked by cheap energy and disposable materials, their approach seems almost radical. We design for speed and convenience, often creating systems that are incredibly powerful but also incredibly wasteful. The ancient engineer, bound by constraints, was forced to design for elegance and longevity. They had to listen carefully to the materials and the forces at their disposal, resulting in solutions that were not just effective, but inherently sustainable. The very limitations we might view as handicaps were, for them, the parameters that guided them toward truly resilient innovation. How might our own designs change if we embraced such limits, not as obstacles, but as the defining rules of a more intelligent game? This unified logic represents the ultimate goal of our reverse engineering. We have examined the individual gears, but now we see the clockwork itself. The ancient engineer's mind was a masterful integrator, weaving together celestial patterns, material properties, social organization, and spiritual belief into a single, coherent system of thought. They did not see a building project as a series of separate tasks, but as a holistic organism where a change in one element rippled through all the others. The choice of a quarry site was simultaneously a geological, logistical, and symbolic decision. The alignment of a temple doorway affected its structural stability, its interior climate, and its religious significance all at once. This was systems thinking in its purest form, an intuitive understanding that everything is connected. The true marvel of the aqueduct is not just the channel or the arch, but the seamless fusion of gravitational physics, public health policy, urban planning, and political messaging into a single, flowing entity. This holistic approach allowed them to achieve a balance that often eludes us today, where a structure could be profoundly durable, perfectly functional, aesthetically magnificent, and deeply meaningful all at the same time. In our specialized world, we often silo knowledge. The architect designs the form, the engineer ensures the strength, the environmental consultant mitigates impact. But for the ancient master builder, these roles were inseparable. This integrated logic is the forgotten template, a powerful reminder that the most enduring solutions emerge when we stop seeing problems in isolation and start seeing them as interconnected parts of a greater whole. How might we reintegrate this wisdom to tackle our own complex challenges, from sustainable cities to resilient infrastructure? The silent stones and intricate gears have spoken, revealing a mindscape where logic was inseparable from life itself. This journey into the ancient engineer's consciousness uncovers a landscape of profound intelligence, one that wove together meticulous observation, deep tradition, and a sacred reverence for the natural world. We have reverse engineered far more than forgotten techniques. We have uncovered a holistic way of thinking that refused to separate the practical from the spiritual, the immediate task from the eternal consequence. Their genius was not in specialization, but in integration, seeing the universe as a single, interconnected system where every decision resonated across multiple dimensions of meaning and function. The urgent lessons embedded in their enduring stones and sophisticated mechanisms are not relics of a distant past. They are a vital inheritance, speaking directly to the core challenges of our time. In an era defined by climate instability and resource depletion, their principles of sustainability, resilience, and holistic design offer a powerful alternative to the short-term thinking that dominates so much of modern engineering. They achieved longevity not by conquering nature with brute force, but by first seeking a profound understanding of their place within its intricate web. True engineering genius, their legacy whispers, lies not in our ability to overpower the environment, but in our humility to learn from it, to collaborate with its forces, and to build in a way that honors the delicate balance of which we are a part. Let this exploration serve as a call to look backward for inspiration as we build our future, to rediscover a wisdom that measures success not in decades, but in millennia. If you found this journey into forgotten logic compelling, share your thoughts on which ancient mystery fascinates you most in the comments below, and subscribe to continue deciphering the secrets of history with us.